What happens when AI meets exact geometry, cross-dialect SQL realism, and symbolic execution traces? In this episode, we dive into 3 papers that push the boundaries of what models can learn and how we evaluate them. One enforces strict compression budgets with Riemannian optimization. Another reveals why SQLite can mislead text-to-SQL benchmarks. And a third shows that formal program traces can teach LLMs deeper semantics. Together, they reveal a striking theme. Precision, not just scale, is reshaping AI research. Let's explore the first paper, Model Compression with Exact Budget Constraints via Riemannian Manifolds. The paper reframes budget-constrained model compression as optimization on a smooth budget manifold in softmax logic space, where the expected cost, C alpha, equals sigma wi softmax alpha, CC, is held exactly equal to a target budget, B. Its key novelty is geometric. The constraint gradient has a closed-form normal vector. Moving logits along the broadcast cost vector C changes expected cost monotonically, and vector transport reduces to a single inner product, so retraction onto feasibility is just binary search on one scalar parameter. Building on this, the authors introduce Riemannian constrained optimization, or RCO, which wraps tangent projection, atom, monotone retraction, and momentum transport around a Gumbel straight-through estimator plus budget-constrained dynamic programming for exact discrete forward passes. This combination eliminates constraint-related hyperparameters and removes the normal component of STE bias before it reaches the optimizer. On a multiple-choice knapsack benchmark with n equals 1,000 groups and k equals 32 options, RCO reaches within 1% of the dynamic programming optimum in 594 steps, while vanilla Lagrangian training stalls at a 37.6% gap and keeps violations around 10, -1, whereas the manifold maintains C alpha B is less than 10, -8. In realistic LLM compression, RCO matches or beats zero-order baselines at much lower cost. On Qwen 330B, A3B, expert pruning, it recovers 96% of the uncompressed benchmark average at 25% pruning, versus 90% for Evo ESAP in about 85 minutes versus 5.2 hours. And on Qwen 3, 8B mixed precision quantization, it cuts FineWeb eDo perplexity to 20.47 at 2.25 bitses, 4% better than EvoPress and about 10 times faster. The method also extends to MOE expert pruning and multi-bit quantization, showing that exact budget enforcement and first-order optimization can coexist in a single Riemannian framework. Let's explore the second paper, PolySQL Scaling Text to SQL Evaluation Across SQL Dialects via Automated Backend Isomorphism. PolySQL addresses a specific evaluation bottleneck in text to SQL. Almost all benchmarks are SQLite based, even though real deployments run on PostgreSQL, MySQL, Snowflake, BigQuery, and ClickHouse. Instead of transpiling gold queries into each dialect, which is brittle and loses semantics, PolySQL migrates the database state with a data load tool and compares the gold query executed on the source database against the model prediction executed on the migrated target database through a normalized comparator that handles ordering, type coercion, and 10, -5 floating point tolerance. Across 16 models, 3 benchmarks, Spider, Bird, and Archer, and 15 dialect environments, PolySQL achieves 100% execution coverage and the best benchmark fidelity against Bird's human transpiled references, with Cohen's kappa equals 0.72, Spearman rho equals 0.75, and Pearson R equals 0.85, outperforming SQL glot-based transpilation and LLM-based judges. Using this framework, the paper finds that SQLite is a poor proxy for enterprise dialects. Performance drops by 10.1% on average, query-level agreement with target dialects is only kappa equals 0.39, and model rankings reshuffle substantially. The failure mode analysis is the key novelty. 61.2% of cross-dialect regressions are logical errors in filtering, joins, aggregation, or grouping, while only 7.7% are pure syntax errors, showing that dialect shift breaks semantic reasoning more than syntax handling. The authors released the PolySQL codebase, migrated environments, and a leaderboard to support dialect-robust text-to-SQL evaluation. Let's explore the third paper, Teaching LLMs Program Semantics via Symbolic Execution Traces. This paper asks whether large language models can be taught low-level program semantics, not just code surface patterns. by training on symbolic execution traces. The authors build a 500 task C verification benchmark from SVComp 2025, spanning memory safety, overflow, termination, reachability, and data races. Then evaluate 14 models and find a persistent asymmetry. Most systems exceed 90% accuracy when a property holds, yet violation detection is much weaker, with 4 models below 50% on violations and accuracy collapsing as programs grow beyond 100, 200 LOC. To address this, they run the Soteria Symbolic Execution Engine over 1 million self-contained C files from CodeParrot, producing about 34,000 traces and training Qwen 3.8b with continued pre-training. The strongest configuration uses just 3,208 manifest bug traces in Soteria's original HTML format, plus Qwen 3's internal chain of thought thinking at inference, improving violation detection by 17.9 percentage points overall, or 26 points on parsable responses, while preserving holds accuracy. The effect is super additive. CPT alone adds plus 7.3 points. Thinking alone gives no gain, but together they substantially outperform the 4 times larger Qwen 332b baseline on violations. Ablations show the gains come from semantic content in symbolic traces, not extra code volume, and that trace format matters. Informalized natural language summaries and plain text conversions underperform structured HTML traces. The main technical result is that formal execution artifacts can transfer general verification reasoning across property types. The training data never explicitly targets. That's a wrap on today's AI paper highlights. Thanks for watching.